Okay, can everyone see my screen? Okay, great. All right, so I'm going to start with a tutorial, which is called Encrypted Computation from Lattices. So they're sort of stealing a name from Daniel Wicks. But let me start with some kind of motivation about why we're looking at all this, one reason why we're looking at all these advanced cryptographic constructions. So we now live in this world of big data where we collect a lot of sensitive data about individuals, financial, medical, customer, employee, and so on and so forth. And one of our concerns is the privacy of this data. Right? This is very sensitive data, and traditional crypto wisdom says that if we want to protect privacy of our data, we can basically encrypt this data. So what encryption essentially does is that it puts the data in a box and basically puts a lock on it, so that only whoever has the key will be able to access this data. Now, the problem is that once this data is encrypted, we lose utility. Without the key, we'll no longer be able to encrypt this data. So what we'll be talking about in some of this new cryptographic construction is a new way of looking at things. This new paradigm, which we refer to informally as encrypted computation, also sometimes known as computing on encrypted data, and so on and so forth. In particular, we'll be looking today across today's talks at three different notions of computing encrypted data. And what's interesting over here is that we're going to show that all of these three notions can be realized from lattice assumptions. And moreover, basically from one single equation. So I'll try to give you a sense of what this equation is and some of these permutation and constructions. All right, so I'm going to begin with the first of these, probably the one of the most famous one in that sense, that of fully homomorphic encryption. So before I define fully homomorphic encryption, let me first just remind you what encryption is. So in the context of this talk, we'll be looking at, or in the context of this construction, we'll be looking at encryption, the secret key setting. So for encryption algorithm and decryption algorithm, both of them share a secret key. Basic functionality says that if I encrypt a value X and then I decrypt to get what we call ciphertext, and if you decrypt the ciphertext after the secret key, you recover your original plaintext X. Basic security says that the encryption of X should hide X if you don't see the secret key. Moreover, this is the secret key setting, so we really actually do require that even if you encrypt many different values under the same secret key X, all of the ciphertext should also hide all of these original plaintext values. So the main difference between, in some sense, fully homomorphic encryption and traditional encryption is the additional functionality requirement, which says that exists an evaluation algorithm or evaluation procedure that takes as input an encryption of X, and any function f produces an encryption of f of X. So the big breakthrough in cryptography, I guess, a decade ago now, is basically that we can actually build fully homomorphic encryption for the class of all circuits from lattice assumptions. So when I first introduced this idea in the undergraduate crypto class in France, everyone was staring at me funny, like, why is this even a big deal? So officially, very much in some senses, like, you know, the internet. So for us, for both of us who were born before the era of the internet, it's like this big thing. For all of you like born in the 90s, this is like something you've always taken for granted. So let me just say that it's actually a very, very big thing. So the early works showed how to construct this from lattice assumptions. That's the first candidate by Craig Gentry. The other two works, after we actually showed, no, not only can we construct it from lattice assumption, we can actually get it from what's called the LW assumption, which will basically be a recurring assumption in this workshop. So what the LW assumption basically says that if I give you a random matrix B, think of it as very wide, and S times B plus noise. This B together S times B plus noise looks random. Right? So basically, noise is what we call E. Think of S and B as uniformly random from some matrices and vectors from whose entries are drawn from some underlying ring like ZQ. And then E you think of as small entries. So this basically says that Gaussian elimination with noise is hard in some sense. All right. So so most of the constructions today will be based on this LW assumption. Sorry. All right. Okay. Good. Okay. In particular, I'll be describing the construction based by Gentry, Saha, and Waters. Sorry. I'm checking to see what the blinking screen says. Right. So I'll be presenting this construction by Gentry, Saha, and Waters. Okay, all right. So, all right, let me try to say what the construction is. As a warm-up first, we're going to basically first show how to build a fully homomorphic encryption if we're willing to ignore the security requirements. So we're going to first build an encryption scheme that's fully homomorphic but insecure. Now, there's a simple way to do this. You don't even need to encrypt the message. The encryption of X is just X. The main difference between this insecure scheme that I'm going to describe and the main advantage of it is that it has more edit distance to an actual secure scheme. Okay. So bear with me, I'm going to describe a scheme that's in some sense needlessly complicated if you don't care about security. But the nice thing is that with a minor tweak, you can actually get a secure scheme. Okay. All right, so what does the scheme look like? The secret key is a vector, a row vector whose entries are uniformly random from some ZQ, which is our underlying ring. So it's row vector, we call it T. The ciphertext is going to be a square matrix. Right, so encryption of X is square matrix A with the property that T times A is equals to X times T. Right? So high school linear algebra says that we refer to T as basically an eigenvector for A with eigenvalue X. We won't really be needing this notion of eigenvector, but we need the equation T times A equals X times T. Okay, so this is basically what our ciphertext will look like. All right. So what we need to do to get this fully homomorphic encryption is that we need to give some evaluation procedure that given encryptions produces encryption of X. Right. So basically, it's sufficient to essentially focus to handle general circuits. It's sufficient to focus on how to handle additions and multiplication. So we think of, instead of being encrypted one value, we think of it as being encrypted many values. Think of X as scalars or bits. Right? So you want a way to give an encryption of X1 and X2, produce an encryption of X1 plus X2, and also to produce encryption of X1 times X2. Any questions so far? So we refer to AI as the encryption of Xi. Okay, so addition turns out to be very easy. If you have two matrices A1 and A2, such that T times A1 is X1 times T and T times A2 is 2 times T, if you add the two matrices up together, you actually get a new matrix, such that T times this new matrix is exactly X1 plus X2 times T. Right, so this sort of satisfies, so A1 plus A2 is indeed, in some sense, a valid encryption of X1 plus X2. So ignoring distribution requirements for now, let's just try to satisfy this correctness equation. All right. Now, how do we then get to given A1, A2? How do we get a new matrix such that T times this new matrix is X1 times X2 times T? Well, basically, we have two square matrices. What can you do to them? We already showed that you can add them. The next natural thing to do is to try to multiply them. It's straightforward to check that if, in particular, T times A1 times A2 is indeed X1 times X2 times T. All right, so the proof is straightforward. You basically replace T times A1 by X1 times T, and then T multiplied by X2, you get X2 times T, and then you get whatever's on the right-hand side. Okay, in fact, by straightforward induction, this scales very well to any polynomial. All right, so for example, if you want to get an encryption of X1 times X2 plus X3 times X4, you basically just multiply A1 by A2 plus A3 times A4. In fact, this scales to any polynomial. This is the one
Hoeteck,
example.
would you like to address the question? Do you see the Q&A window?
No, I actually don't get the Q&A window. Sorry, I will have to figure out how to.
So there's a question in the Q&A window. Until then, let me repeat that for you. How is encryption of secret key comma X defined?
How is encryption of secret key comma X defined? Good, that's a good question. All right. For now, think of what's the distribution? So the output of encryption of T comma X is a matrix A such that T times A is X times T. So so in some sense, I haven't said what the distribution for T is. Think of it as picking a random uniformly matrix A such that T times A is equals to X times T for now. Okay, so pick a uniformly random A that satisfies this equation. Questions? I can't figure out how to show the Q&A window at the same time. So Zvika, you may have to repeat the questions to me for now. All right. So the nice thing about this is that it scales to any polynomial. In fact, if you have any polynomial f in n variables, T times f of A1 to AN is exactly, in some sense, an encryption of f of X1 to Xn. All right. Now, how do you even apply a polynomial to matrices? Think of the naive, which is basically the generalization of this. Just replace each of the variables with the corresponding matrices. Okay. Now, there's a little bit of subtlety here in the sense that matrix multiplication is not commutative, but let's just fix some ordering. Let's say always multiply in the lexicographic order, and then that gives you a way to apply a polynomial to matrices. In fact, it doesn't really matter how you handle the multiplication, whether you do A1 times A2 or A2 times A1, you still get a polynomial such that T times that polynomial is X1 times X2 times T. Okay. So that's a natural way to define F applied to all of these matrices, and that basically is what the FHE evaluation is going to be. Any question at this point? Okay. All right, so now let's try to fix this scheme. So this scheme is satisfy functionality, but it satisfy security. So let's try to fix this scheme so that you get security. Along the way, we're going to lose functionality, and then we'll try to fix that later. Okay. Now this sort of goes back to the earlier question, the question from Q&A. If you care about security, it's actually very important to exactly precisely say what the distribution of encryption of XKX is going to be. All right, but let's just say for now that to get security, basically we're going to add noise. Okay, the intuition is that it's actually not hard to see that the previous scheme is completely broken by Gaussian elimination. And the intuition from the LW assumption is that if you add noise, then you can get a secure scheme. All right, so this is roughly what we're going to do. We're going to say precisely how to carry out this distribution later, but basically now an encryption of xi is no longer going to be a matrix such that T times AI is exactly xi times T. It's going to be the case that T times xi is close to xi times T. All right, what does close mean? Close you should think of as sort of close in I guess L infinity norm. So the difference of the two of them is small vectors. Each of those entries is small. Or you can think of close as being the difference being the noise distribution from the LW assumption. Are there any more questions? Okay, so intuitively, this is the distribution that we're going to be looking at. We'll say a bit precisely what this distribution is going to be. But turn out, basically, if you add noise, then you can show that basically given AI or many AIs, you learn nothing about the underlying XIs. All right, so this gives you security. Let's try to see whether what happens to functionality. All right, so at least for addition, things still work. Now, if you're given two matrices such that T times A1 is close to X1 times T, and T times A2 is close to X2 times T, then T times A1 plus A2 is still close to X1 plus X2 times T. Basically, this is because when you add two small values, you still get a small value. Now, the new small value you get is going to be slightly bigger than the previous small values, but let's ignore this distinction from now. All right, small is small. There are different notions of small, but let's just take them as all of them as being small for now. We'll come back to this a bit later. Now let's see what happens when you do multiplication. Right. Turns out if you try to naively proceed as before, if you just multiply A1 times A2, then T times A1 times A2 is actually not going to be close to X1 times X2 times T. And the reason basically is that the small from T times A1 gets multiplied into A2. Think of A2 as a uniformly random matrix. So each of these entries is uniformly random from ZQ. And in general, uniformly random from elements from ZQ are going to be big. Right? So A2 is basically going to be big. So when you multiply small by big, you're going to get a big value. Okay? So you don't quite get correctness anymore. You can handle addition, but you cannot handle multiplication. So here's where the next idea comes in. We're going to make AI small. Okay? Now think of AI as instead of a uniformly random matrix such that T times AI is close to Xi times T, it's going to be a uniformly random matrix with small entries. Now at this point, it's not even exactly clear if such an AI exists, but let's pretend for now that such an AI exists. You can sample small AI such that T times small AI is close to Xi times T. Right? So we somehow manages to enforce that the AI have small entries. Okay? Then the previous problem goes away. Now, if you look at small times A2, A2 is now small. So now T times small times A2 is still going to be small. And that allows you to argue that T times A1 times A2 is close to X1 times X2 times T. Okay? So that sort of solves our problem. So now what do we end up with right now? What we have now, oh sorry, this also, since we already had the additional multiplication for the same reasons before, this scales to any polynomials. Right? So you can ensure that T times f of A1 up to AN is close to f of x1 up to xn times T. Right. So what have I done so far? Right. What have I done so far? Basically, is to give you a template to build a fully homomorphic encryption scheme. All right, what does template say? The template says I need to come up with the following. I need to come up with a distribution for secret keys, which are row vectors T. I need to come up with random small matrices A with the property that T times A is close to X times T. That's the first basic requirement, sort of a generalization of the eigenvector approach to this approximate setting. And we need two additional properties. We need that A hides X, this gives you security of the encryption scheme. And we need that A, the entries of A are small. This gives you homomorphic multiplication. All right. So if you can get all of these three properties from some reasonable assumption, lattice assumptions, then you get an FHE scheme. So we have reduced this general problem to just satisfying these three properties. All right. So So how are we going to? So I'm actually going to show you how to get all of these three, how to satisfy all of these three requirements. Again, starting from just LW assumption, and sort of like before, we're going to try to sort of satisfy some subset of the requirement first and ignore the other ones and try to fix it. Okay. All right. So first, we're going to try to satisfy the first requirement, which is T times A is close to X times T. Okay. All right, so what does T look like now? T is not going to be uniformly random vector over ZQ anymore. It's going to basically be, the first half is going to be uniformly random. The final entry is going to be -1. Okay, note that I put an S here. The S basically is the distribution of the secret S in your LW assumption. Okay, now our ciphertext, we're going to try to build the scheme from the LW assumption, so we have to put in LWE assumption type challenges somewhere. So the ciphertext is going to look sort of like the LWE assumption, the quantities in the LW assumption. So there's going to be a matrix B together with S times B plus E. Okay, remember that this quantity over here by itself is pseudo-random if you don't know what S is. Okay, now the secret key. Now note that if you multiply the secret key S-1 by this quantity, you get something that's small. Now this is our secret key, which is going to be T. I want I don't want 0 on the right hand side. I want X times T on the right hand side. Okay. What do? I basically add X times I to this quantity over here. Right? By linearity, this times this is small, this times this, T times Xi is basically X times T. Okay, so I've satisfied my basic requirement, which is T times A is close to X times T. I'm going to call this quantity over here my A, basically. Okay, so I satisfy my first requirement. In fact, also satisfy my second requirement, which is that A hides X. By the LW assumption, this thing looks uniform. And then uniform plus X times I is uniform. So this whole thing looks uniform. Okay, so I satisfy my second requirement. The problem now is that, this is my A, and I need to somehow make A small. Okay. By the way, I'm doing, I think, pretty well on time, so I'm happy to take questions. All right, so I need to make this A small. Okay, I may have a question. Speaker, is that a question? I see one.
Yeah, so there's a question whether X is a bit, which...
Good. Okay. Yeah. So early on when we talk about, that's a good question. Early on when we talk about the basic eigenvectors, I think we know it's not the insecure scheme. X can come from ZQ. Henceforth, we're basically going to work with X being a bit. Okay. It hasn't quite come up yet, but let's just say that's sufficient to handle X as a bit.
Okay. There was an additional question about the smallness of the matrix A, which I assume that you're going to get to next, so I did not bring it up yet. So if the person who asked still has the question after the end of the slide, they can bring it up again. Okay. And in general, if you see that you raise the question that's already been answered, then just try to dismiss it just so that we know that that you're fine.
I'll try to also pause ever so often to take questions. Right. So this is our A. All right. Before the problem is that A actually has large entries because this part over here, the B. When they think about the LW assumption, you should think of B as coming from uniformly random entries, right? So this is going to be big. We also want this to be pseudo-random, so this also has to be big in that case. Okay. So this whole thing is big. So A now has big entries. Okay. Now we want to make A turn A into a matrix of small entries. In fact, we're going to do something more general. We're going to, all right, so that's next. We're going to show how to make A small. Ignore for a moment how to get A to hide X. Okay. Now we're going to make A small. In fact, we're going to give a generic transformation that takes any matrix over ZQ and turn it into a matrix of small entries. In fact, we're going to give you a generic matrix, transformation that takes any matrix M, any arbitrary dimensions, can be rectangle, can be square, can be vectors, can be whatever you want, and turn it into a matrix of small entries. Okay, how small? The entries here are going to be actually 0, 1. So how do you get to something where entries are from ZQ to something at 0, 1? You basically want to take the binary representation of M. Okay, lattice literature is called bit decomposition. So we want to take the binary representation of a matrix. What does it even mean to take the binary representation of a matrix? Okay, so first we're going to take, so basically what's going to happen is that this new matrix that we're going to get is going to be, has much bigger dimensions. The height is going to be log Q times the dimension of the original matrix. Okay, the top part is going to be stacked in a specific way. The top part of this new matrix is the least significant bit of the matrix M. What is the least significant bit of a matrix? It's basically the least significant bit of every entry of the matrix. Okay, entry-wise least significant bits. The bottom of the matrix is going to be the most significant bit of the matrix. What does that mean? Entry-wise most significant bits. Okay, so the second block is going to be the second bit, and then the third bit, the fourth bit, right up to most significant bits. Okay, so in general, this thing is going to be basically the matrix on the right is going to be look like basically log Q blocks of matrices. Each block has the same dimension as the original matrix. The first block, the topmost block, is the least significant bits of each of the entries, and so on and so forth. Okay, this gives you a generic way to take any matrix and turn it into a matrix, 0, 1 entries that in some sense contains the same information. Right? Now, in general, this transformation is actually not going to be linear. Taking bits, computing bits of a number is essentially not a linear operation. But what is nice, however, is that the inverse of this computation is actually linear computation. In particular, if I have this sort of this binary representation of a matrix M, I can recover the original matrix M by left multiplying this matrix by another matrix. Okay, so this is a linear operation that goes from this matrix to the original matrix over here. Now, what is this matrix that I need to multiply by? I need to multiply by a very wide matrix. The dimensions is to match up. And what are the entries of this matrix? The first half is going to be sort of blocks of matrices. The first block is going to be I, 2 times I, 4 times I, up to Q over 2 times I. Okay, what happens when you multiply this matrix by this? You basically get the least significant bit times I, the second bit times 2, the third bit times 4, and the most significant bit times Q over 2. And that basically exactly gives you basically multiply by powers of 2, and then you get back the original matrix M. Okay, so what's nice here is that even though going from this representation to this representation is not linear, you can go back via linear transformation. All right, so this is actually just matrix multiplication. We're going to call this G, which is what's called the gadget matrix in the literature. And because this times G is this matrix over here, following literature, we're going to denote this matrix over here by G inverse of M. Okay, let me stress that G inverse of M is not the matrix inverse of G multiplied by M. Rather, you should think of it as this binary representation. You should think of G inverse as a function applied to the matrix M. We call it G inverse because G times this thing gives you M. Any questions? Is that a real question, or I see a 1 on top of the Q&A? I should try to figure out if I can. Okay, so let me carry on for now.
So maybe I'll read the question. The question is, do we need this transformation because there's no LWE for small a?
That is a very good question. All right. Okay. The question is good. The transformation is actually good. Basically, we want something to be small, right? So if you look at this thing over here, maybe LWE holds even B counts of small entries, but you need this SB plus E to look random. So there's no way SB plus E is going to look random if it's going to be small. Okay, so roughly speaking, you need this transformation to get to something that's small. In fact, roughly speaking, if you want to prove LWE for if you want to prove the LWE for small b follows from uniformly random b, you're actually going to apply this transformation as well. Okay. All right. So sorry, so now we have this transformation, and we're going to apply this G inverse operation to our matrix over here. Okay, so let's apply G inverse to this thing, and this gives you a way to make sure that my A is small. Right. So I still want to maintain this quantity over here. So if I apply G inverse to this quantity, I need to multiply G back. All right. So if I put in a G and a G inverse, I still maintain the same equation. And now this G inverse will enforce that all of these entries are small. So this is going to be the G inverse of whatever used to be our A will be our new A. And now we guarantee that A is small. Okay. But now we have a new problem, which is that this is our T, there's some G over here, and there's a T on the right-hand side, and this G needs to somehow, disappear. Okay. So turn out the right thing to do is that I can replace this I by G, and then I get TG on the right-hand side. To replace I by G, I becomes wider, so you actually need the B to be much wider. But that's fine. LW still holds. So now you have TG on the left-hand side and TG on the right-hand side. You just call TG your new T. Okay, so now we satisfy everything. Right? So our new T will basically be S minus 1 times G. This will be our A. Okay, and this satisfies the equation this time. This is X times T. We get that A hides X because by the LW assumption, this is uniformly random. When you apply G inverse, it doesn't leak any more information. And we have the A is small because G inverse is applied to this quantity over here. Okay, so this is basically our final FHE scheme. Any questions? Okay, so basically I've shown you how to build an FHE scheme. Let me just take a quick detour to talk about this issue of small. I'm going to try to make this a bit quick. It's sort of orthogonal to the rest of the tutorial. So I talked about how small values are small and that there are different notions of small. So in general, what will happen is that if we actually multiply two matrices together for homomorphic multiplication, we actually end up multiplying basically G inverse applied to something multiplied by G inverse multiplied by something else. Now, in general, G inverse, if applied to anything, is going to have entries that are 0, 1. When you multiply two matrices at 0, 1, you actually get something that's a little bit bigger. It actually grows by basically the dimension of the matrix. So if you do multiplication this way naively, the final small that you get from your after you apply a polynomial of degree f, is your new small is going to grow exponentially in the degree. Okay, right. Okay, just to quickly backtrack. Why do we care about the how quickly small grows? Because basically the how small the final value is going to be will basically affect how big the modulus is going to be for correctness, and this in terms affect the basically the kind of assumptions we need to make for LWE. We basically want small noise growth to get, in some sense, quantitatively weaker assumptions. Okay, so if you do things this way, it will grow with degree of f, which turns out not to work very well. What you want to do really is basically instead of applying G inverse to M1 times M2, whenever you want to multiply two things together, you basically apply the G inverse after you do the multiplication. So you apply the G inverse to M2 first, multiply M1 by this, and then do G inverse at the very end. This ensures that the final output will still be 0, 1 entries. Note that both of these equations satisfy the property that when you multiply by G, you get back the same value for both of this. And by sort of reordering your G inverse operations, you can actually get a noise growth that's exponential in the logarithmic of the degree. And this turns out to be the right thing to do for circuits so that you grow exponentially in the depth of the circuit. Okay, this is one idea to get smaller noise growth. I want to just quickly also mention a second idea to get small noise growth in the context of lattice-based crypto. So the way I describe the scheme so far when I talk about polynomials, we're really basically essentially working with arithmetic circuits.
Hoeteck,
yeah,
it was a little too fast for me. Can you go back one slide?
Yeah, sure.
Given that you have time also. Okay, so what are you saying here? How did you get over the? How did you get to the logarithmic power?
Good. Okay, so I slightly cheated, but so what is the difference between both of these equations? They both satisfy the property that G times the whole thing is M1 times G inverse of M2. So if you do it this way or you do it this way, you still get to the property that G times blah if M1 times M inverse of M2. The difference is that if you do it this way, you get the product of 2, 0, 1 matrices. Your new matrix is going to grow basically the dimensions of the two things. Whereas if you wait, you multiply first, then do your G inverse, the output of this will always be 0, 1 entries. So somehow your noise grows a little bit slower. in fact, logarithmically. The exact details doesn't follow quite from this equation. There are this noise and so on and so forth, but this is the basic idea. You want to reorder your G inverse operations in a way that helps you grow more slowly. Okay, all right. So that's a second idea that's also used in the literature on lattice-based crypto, which is basically what I said so far. When you work with polynomials, you're basically working with circuits. The thing about circuits is basically that, so we're actually working with arithmetic circuits. So you're going to have this addition and multiplication gates. Addition gates turn out to be okay, not a big problem. The main issue with this big noise growth come over multiplication gates. Now, when we're with circuits, what's basically going to be happening is that a circuit has, the circuit model of computation has the property that you always essentially multiply values from two intermediate computations. Okay. And basically this causes a phenomenon where basically every time you do a multiplication and you have a multiplication gate, you basically double the noise. And this creates a phenomenon where the noise is going to grow exponentially in the depth. Okay. Turns out it's much better to work with branching programs. The basic property that we have of branching program is basically a branching program has a property that in each step of the computation, you always sort of read one input bit, look at where the intermediate state you are in, and then proceed to the next step. Okay. So what happens when you translate this into the FHE setting is that basically you never multiply two intermediate values. You always multiply intermediate value by an input value. Okay. Now the input value, you can guarantee that the noise is fixed, is very small. And now your noise only multiplies the intermediate noise by the input noise. So it starts growing a lot slower. In general, what happens when you work with branching programs is that your noise will grow with the length of the branching program. Okay. Now recall that if you have a circuit of logarithmic depth, it can be simulated by a branching program of polynomial length. Now, what this happens now is that if you apply sort of the naive approach to work with circuits, you get a noise that goes exponentially in depth, so you get an n to the order log n blow up. Whereas if you work with the branching program, since the noise is polynomial in the length, you get a poly n blow up. So that's really an advantage of working with branching programs. And this is the same phenomenon actually that underlies some of the more recent work on this function secret sharing from DDH for branching programs, sort of this exploiting this asymmetry in the way we handle branching program computation. And this basically allows you to get FHE for log depth circuits with a polynomial blow up, so you get under polynomial hardness assumptions. And the same idea also works for ABE. Okay. So now I described essentially two ideas to control noise growth. One is to reorder the G inverse, the other one to work with branching programs instead of circuits. Okay, so this takes care of all the small values issue. But okay, so all the small.
Sorry, can you just explain maybe for the larger audience what polynomial hardness means?
What polynomial hardness means?
Yeah, use the term. So.
I see. Okay, right. So in general, right. So the RWA assumption, in some sense, actually in some sense a parameterized assumption. So the hardness of the RWA assumption actually has a parameter, which is basically the ratio of the noise, the ratio of the underlying modulus of the noise, and you want this quantity to be as small as possible. Basically, the assumption is weaker if the ratio is polynomial, and the assumption is stronger if the ratio is, say, sub-exponential. This sort of makes sense because, you know, when the ratio is big, you're actually adding very, very small noise. Okay. So polynomial hardness means that you're in the regime where the ratio is polynomial. Okay. And the polynomial comes from the fact that this ratio, the ratio that you need basically comes from the blow-up in the noise when you do your computation.
So Hoeteck, perhaps since you've been going over some pretty technical stuff, if there's additional questions from the panelists or from the audience, I see that there's I guess one in the Q&A section asking if there's a price that you're paying for using branching programs. Like, why wouldn't you? Is it always better to use branching programs than circuit?
Good. Okay, good. So remember that the branching program is actually a weaker model of computation. When you convert a circuit to a branching program, you get a blow up that's exponential in the depth. So, so when you work with branching programs, it's actually in sometimes weaker in terms of expressiveness. You can only handle log depth circuits. Right? But the nice thing is that you get a smaller noise group. Okay, so whenever you're dealing with log depth circuits, it's better to work with branching programs. But results for branching programs do not imply results for circuits, because the weaker model of computation.
So perhaps can you say something if you can always convert a computation into a branching program? Are there cases where you cannot do this?
Right. So in general, if you have a circuit, you can convert to a branching program with a blow up that's exponential in depth. So if your circuit has depth that's super logarithmic, your branching program is going to have super polynomial size. So in that sense, you can only convert logarithmic depth circuits.
So perhaps the participant would like to know what you do when you do have circuits with sort of super logarithmic depth. How do you do homomorphic evaluation? That kind of circuits.
Right. So you basically should stick to the original scheme where you handle where you basically you essentially convert a circuit into a polynomial and then just work with the polynomial. One should be a little bit careful what you mean by converting a circuit to a polynomial, but basically you do what you do. You look at the arithmetic circuits. Whenever a multiplication gate, you multiply the ciphertext together. Whenever addition gate, you just add the matrices together. All right. So I make this detour into talking about small. This is something that we won't be using for the rest of the talk. I want to go back to our original sort of FHE scheme and this view of looking at things as eigenvectors. Okay. So, right. So I won't be coming back to the small issue anymore. If anybody has questions about the small and noise flow, or we can just take them to the end of the talk. Okay. Let me come back to this eigenvector issue. So basically, the crux of this fully homomorphic encryption scheme really boils down to what happens before you introduce noise. So the magic of it is sort of this algebraic phenomenon that says that if I have a bunch of matrices, and the vector t, such that t times ai is xi times t, then t times af is f of x times t. Okay, where af is the shorthand for f applied to these matrices a1 to an. Okay, this sort of this simple algebraic identity that sort of follows from high school linear algebra sort of gives us all of this magic FHE scheme. Relax the approximation value. All right, so now I want to, we already gave one generalization of this in some sense, where we go from exact equality to approximate equality. Now I want to show you a different generalization. Okay. But before that, let me rewrite this equation as saying, sort of, moving terms from the right-hand side to the left-hand side. This basically just says that t times ai minus xi is equal to 0 implies blah, 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 blah. Okay, these are the same thing, just moving things to the left-hand side. And this holds for any polynomial, right? All right, now I want to generalize this thing. In what sense? So this is a statement about matrices A1 to AN that share the same eigenvector T. Okay? I want a generalization to this statement that does not talk about eigenvectors. I want a generalization of this statement that applies to any matrices A1 up to AN. Okay, why is this useful? Is useful. Okay, let's just try to generate this statement. All right, what could this statement potentially look like? So there's no t anymore. So basically, I want to relate the terms on the left-hand side to the terms on the right-hand side. Okay, so on the left-hand side, I'm going to have a1 minus x1i, which corresponds to this term up to x and a1i. On the right-hand side, I have af minus f of af minus fit. I want a statement that implies a statement that I call lemma 2 that implies lemma 1. Okay, so here's the statement. I will tell you what the statement is, and then we'll convince ourselves that it implies lemma 1, and then I'll show you how to prove lemma 2. Okay, so here's our new lemma 2. Okay, the new lemma 2 is going to say that if given a bunch of matrices and any x, so x1 up to xn, and any function f, in fact any polynomial f, that exists some matrix H. This matrix H is going to depend on, by the way the order of quantifier goes, it's going to depend on the A matrices, the X and the F, such that H multiplied by this stuff over here is equal to the right-hand side. Okay, this is the this I claim is the correct generalization of lemma 1. Okay, let me first convince you that lemma 2 is indeed a generalization of lemma 1. So let me first convince you that lemma 2 does imply lemma 1. Proof, well, just multiply both sides by t. Okay. If you multiply both sides, if lemma 2 is, I'm going to prove that lemma 2 implies lemma 1. I'm not, at this moment, I'm not proving that lemma 2 is true. Let me just do a sanity check that lemma 2 is indeed a generalization of lemma 1. So lemma 2 implies lemma 1, why? If you multiply both sides by t, t times the left-hand side is going to be 0, thanks to this. 0 times h is 0. So the right-hand side is 0. So t times the right-hand side is 0, which implies this statement over here. Okay, all right, let me pause for a moment and take questions.
Yeah, there's a few questions. The questions about the sort of branching program, still the conversion from circuits to branching program and when it's useful. So the first one is whether you can do this type of conversion also.
Is it okay if I take all branching program questions to the end of the talk?
Yeah, so let's just do that.
Yeah. Also, it's sort of model computation and sort of orthogonal to lattices. Okay, so if you guys don't mind, I realize I can actually figure out what the questions are. Okay, they're all related to noise growth and branching program. Let me take them to the end of the talk.
Are there any questions? Yeah, but if you want, we can try to see if there's questions that are related to the current slide.
Okay, I think there are no questions for now. So this is so this statement is somewhat complicated looking. So I want to the first sanity check is to check that 2 implies 1. So it's a right generalization of lemma 1. Okay, so I hope I convince you that 2 implies 1. So all right, so I have shown you the proof of 1. I have shown you that 2 implies 1. Just because 2 implies a true statement doesn't imply that 2 is true. Okay, so I actually have to show you that lemma 2 is actually true. Okay, in particular, I need to show you how to construct this matrix H. All right, so let's try to prove lemma 2. Okay, I'm going to follow as before in the FHE setting. If you want to prove any statement for polynomials F, we're going to just do it for addition and for multiplication. Okay, all right, let's do it for addition. Good. So what does the statement look like for addition? All right, remember for addition, and I'm going to do it, sorry, I'm going to do it for addition, for multiplication, I'm going to do it only for n equals to 2. Okay, so this is what it looks like. The left hand side looks like this. A sub f for addition is just
just to slow you down a second. So what's n here? Is this the number of operations?
Sorry, yeah. N is the number of bits in the input. So you think of it as operating on n ciphertext. So you're computing on n bit string. Yeah.
Okay, so now we have a function that takes n bits.
Yes. In fact, this statement holds for x1 to xn, even if they come from ZQ. So you have a polynomial n variables.
Yeah.
F is a polynomial n variables. And I'm going to prove this statement for n equals to 2. So for polynomials in 2 variables, I'm going to prove it for 2 special polynomials, addition and multiplication.
Okay, so x is x1 through xn, yes?
X is x1 to xn, yes, that's correct.
Your notation, okay, fine.
Yes.
Mm-hmm.
So this is x1, x2. This is what the left-hand side looks like. AF for addition is just a1 plus a2. F of x is x1 plus x2. So I need to come with some h such that this times this h is whatever is on the right-hand side.
Sorry for these trivial questions, but they these are very...
Yeah, good. Yeah, another good question. Okay, so let's see. Does anyone want to give it a shot? Okay, so there is a question. Let me just quickly answer the Q&A question. Okay, there are 2 questions. Okay, there's a question about instance of SIS. Okay, this statement is an algebraic statement. Yeah, lemma 1 and lemma 2 are algebraic statements. They're not about computational assumptions. So I'm going to put questions related to SIS later on. This is algebraic identity. Nothing to do with assumptions. Okay, nothing. This statement had nothing to do with LWE, nothing to do with SIS. The next question is lemma 2 true for any field? Yeah, actually, lemma 2 is true for any field. For any ZQ, any ring, and any field. Okay. All right, so let's try to prove lemma 2. Okay, sorry, that's the second part of the question. Okay, then you have polynomial. The polynomial is basically the polynomial, over the ring. Okay, let's try to do this for addition. Okay.
Hoeteck, perhaps when you refer to the question about whether the equation is true over any field, you can relate to the issue of smallness of H. How does this condition translate to different fields?
Good. To be clear,
not?
That as this H, H doesn't have to be small. They just have this H. Yeah. Yeah. So this statement is nothing to do with small. Good question. Okay. This statement, well, back in the setting, we don't care about noise for now. We don't care about security. We just want to see what the statement is. Okay, so there's no notion of small here. Yeah, this is really an algebraic statement, nothing to do with lattices, nothing to do with anything, just algebra. Okay.
So if you just, so is there a sort of a trivial way to see it without constructing H? Is it?
No, the statement is about H, right? So the statement is that as this H, so you need to construct H. the statement that exists a matrix H. Yeah, so we need to construct the matrix H. The lemma explicitly talks about the existence of matrix H. Maybe you can prove the existence of the matrix H without explicitly writing down the matrix H. But for
the question is, so you're saying even just the existence of the matrix H is non-trivial and requires proof to show.
Yeah.
I guess it's a definition of H together with the definition of A sub F.
Good. Okay, good. Let's pause for a second. Okay, so formally speaking, for to be useful, you actually need this H to be computable in polynomial time. Okay, but let's ignore the fact that you need to be computable in polynomial time. Whether H exists at all actually needs a proof. What is A sub F? Okay, A sub F here is still whatever A sub F we have used before. Yeah, F applied to A1 up to AN. Okay? With some appropriate canonical ordering for multiplication. So A sub F is well defined. So the only thing that I haven't specified in this lemma, so the A sub F is well defined. The only thing I haven't specified in the lemma is how you construct this matrix H. This should hold again over any field. Okay. Any question?
Yeah. Question. So if you just wanted the existence of such an H, right? H can depend on F, X, and the A's.
Yes.
So you can solve a linear equation. So this thing that you wrote down in lemma 2 is a linear equation. You can solve it and you can get an H. So there exists an H, but presumably you want something with a nice property.
True. No, not completely clear that a solution to H exists, because if you work out the dimensions, it's not quite clear that H exists. Right. A linear system, you can solve a linear system if a linear system can be the case that when you try to solve a linear system, there is no solution. Okay, so if you can, you need to at least prove that the linear system has a solution.
True, but A1 up to AN minus XI is a wide matrix. Each A is a wide matrix, right?
No. Each A is going to be a square matrix for now.
Oh, each A is a square matrix. So if you put two of them together already, you get a wide matrix. So in terms of just kind of sanity check, there might be a solution.
Right. There's a sense. Right. Yeah. It's not obvious that there is no solution. Right. Yeah. But it is also important again for the applications that we need that H is efficiently computable given the A's and the X and the F's. So it's useful to have a sense of what a closed form expression for each looks like.
Right. Okay. That's what you. Okay. Mm-hmm.
But even before that, you need to make sure that the linear system has the equation, has a solution.
Sure.
Okay. Good. So I mean, if the right hand side is 0, then by counting dimension, that is a solution. But the right hand side is not 0, so not all inhomogeneous linear system has a solution, even if the dimensions match.
A random one probably does, but
yeah, but we want this to hold for all A's, so and for all X's. Yeah. Okay, good. So let's try to solve this. Now it's not so bad. Yeah. So for addition, turns out it's really easy. Basically, you just stack two identity matrices together. Okay? So this times this times this. So the right hand side is basically if you add these two matrices together, and then you get the thing on the right hand side. Okay. So multiplication is a little bit more interesting. Again, okay. So now you want this times this is A1 times A2 minus X1 times X2 times I. Okay, good. So what are we going to do? We're going to good. Okay, we're going to try to make this part match up. So I'm going to take A1 and multiply by A2 over here. Okay, and then now I need to fill in the bottom part so that you get the thing on the right hand side. And turns out if you put Xi times X1 times I over here, you get exactly what you want. Okay? So X2 times X1 gives you X1 times X2, and basically you get cross terms actually X1 times A2, but it cancels out with cross term A2 times X1, and you get exactly the right hand side. Good. I think there are no questions, and this basically gives you the construction for H for addition and multiplication. Okay? So note that this H actually depends on X and the A's. Okay? So I claim that once you handle addition and multiplication, you can handle any polynomial. For the proof of lemma 1 is straightforward, it's just an induction. For this proof, you actually need a little bit of care. It's not immediately obvious that you need to somehow glue all these matrices for H for addition and multiplication together to work for any polynomial. This gluing is a little bit more non-trivial than the gluing for the proof of lemma 1. Okay? Let me just say that. Yeah.
Hoeteck, how do you want to organize the rest of the talk in terms of time? Because we have a break scheduled coming up.
I have to, oh wait, now I lost track of time, sorry. Can you tell me how much time I have left?
-2 minutes, but
oh, no.
you know, we're all friends here.
Oh, I see. Okay, all right. Sorry, I lost track of time. Okay. Let me finish in 5 minutes, I think.
Yeah, that sounds all right.
Okay, good. So, right. So let me just say that basically, you actually need a stronger version of this statement, which basically you want a statement where you basically replace your matrices AI by a wider matrix AI, and you replace I by the gauge matrix. You get a stronger version of this statement where you can guarantee that H has small entries. Okay, and this is exactly what's going to be useful. Right, so I'm going to skip the proof, basically, but at least explain why you want H to be small. Okay, the reason why H is small is useful is that it gives you an equation that's robust to noise. So what this means is that if on the left-hand side you have this quantity plus noise, the noise multiplied by the H, and then you get something approximately close on the right-hand side. So if you have a version where H is small, it gives you a version of lemma 1 for approximate equality. Okay, and the proof is going to be and you get equation of this kind, and the proof basically as before you do additional operation, so you have to be a bit more careful when you do the G inverses. So I'm going to skip this part. So this equation has a couple of applications already. We have seen applications to FHE scheme. Basically, if you look at FHE scheme, the A sub F is basically your evaluated ciphertext, the ciphertext you get after actual evaluation. You use the H matrix actually not in any algorithm, but to argue the correctness of the scheme. Okay, so later today you will see somehow how this equation comes up in building ABE and fully homomorphic natures, where the matrix A sub F and H sub Fx plays different roles. By the way, for those of you playing bingo, the tutorial doesn't count. The bingo starts after the tutorial. Okay? All right, so to conclude, all right, so today we have seen Today we have seen and we'll continue to see how starting from lattices you can do encrypted computation. At the heart of this is the following equation, where now I is G and this H is guaranteed to be small, and you get this relationship. Okay, you won't quite see this in today's talk, I don't think, but in some papers you will see that instead of a minus sign, you get addition sign. They're basically the same thing, what we call tomato. So don't worry about it if you see a minus or plus sign. Also, today we have seen that starting from lattices, you can build FHE for circuits with the property that decryption is extremely simple. In fact, decryption is basically multiply T by A. So decryption basically is just computing an inner product. Okay? This turns out to be building FHE scheme with simple decryption turns out to be terribly useful. So a series of work shows that basically you can use FHE to sort of do some kind of bootstrapping. So if you want to build some primitive X, for circuits, it's basically sufficient to build this primitive X for FHE decryption. Okay. So this idea has been used in the context of functional encryption for bounded collusions, one key functional encryption, and also in the work on predicate encryption. In fact, among this work, the last one uses not only that specifically uses the fact that FHE decryption is an approximate linear function. Okay, this turns out to be a very powerful idea that we first used in predicate encryption. And tomorrow you will see this idea being used as a starting point for building new simple construction obfuscation. New construction obfuscation from simple assumptions. Right, that's going to be a theme for tomorrow. This starting point, and there are a lot of very nice ideas that you'll hear tomorrow. Right. So today I showed you a specific way of, in some sense, having an equation that sort of encodes computation into matrices and lattices. On Wednesday, you will see a different way to encode computation to lattices. This so-called underlie was called the GGH multilinear maps. You see a new way of encode and a bunch of applications again to candidate obfuscation, traitor tracing, and lockable obfuscation. Thursday, we'll see a collection of slightly different topics. We'll see connection between lattices and MPC. We'll revisit the LW assumption, and we'll also look at FHE in a multi-key setting. And on Friday, of course, any lattice workshop won't be incomplete without some connection to quantum crypto. All right, so let me first thank everyone, and then maybe you can all start your breaks, and I can take questions during the break. Thank you. Zivika, maybe you want to say when we will resume?
No, I want you to first look at the Q&A and see if there's questions that you would like to address before we adjourn this session, and then we'll take a break.
During the break. So
I think maybe if you see that there's questions that could be beneficial for much of the audience, then you can take them now if you wish.
Okay. Slides will post them. The branching program, I guess we should probably just take them offline. They're not urgent. Lemma 2 is strange. Let me take a look a bit later. The general lemma gives vector FHE. Okay, I'm going to skip that question. Lemma 2 is strange. Let me address this. Lemma 2 is strange. Good.
Can you also repeat the question just so that it's also available in the recording?
Yeah. So one question was, lemma 2 is strange in the following sense: if the matrix H is not used in the scheme anywhere, how is the H useful? Okay. So it's conceivable that even though H is not used in the scheme, H is used in the proof of security or the proof of correctness. In particular, if you look at the proof that lemma 2 implies lemma 1, we actually use the H. We use the fact that in the proof of 2 times 1, we use the fact that 0 times H is 0. So in the proof of 2 lemma implies 1, we actually already use H. In the more general setting, we're going to be using the fact that, in the proof that lemma 2 star implies lemma 1 star, which is when H is small implies approximate version. We use that H is small because when H is small, this implies that T times this is small. Small times a small H is small, so T times this is small. That gives you the right hand side. Okay. So even though H doesn't appear in the scheme, you can still think of ways in which you use H. Okay, so the proof of lemma 2 implies lemma 1 uses the fact that H is small, and lemma 1, roughly speaking, is the lemma that's used in the correctness of the FHE scheme.
All right, so I guess other questions, you can contact Hoeteck, or you can actually, Hoeteck, if you wish, you can just go to the Q&A window and answer the individual questions. But let's take a break. Let's take a 10-minute break.